Oh, thank you, Arip. Almost forgot. So yes, what type of force we'll be expecting to experience on this surface? Our part is rotating this way. So we would expect a force acting in this direction. So this is a tensile force. All right. So we first have to solve for the value of our force. Again, torque is equal to force times distance. Force is equal to torque. Torque is equal to force times distance. So our force is equal to our torque divided by our distance. We know our torque from our torque analysis. Distance is the one that we're not sure about. So the distance is the distance from the center of the shaft, the center of the hub thickness above the key. That's the distance that we're taking. So distance will be equal to the shaft radius plus key height divided by 2, because half of the key is protruding above the shaft, plus our hub thickness divided by 2. All right, and this is an assumed hub thickness. So you can assume any thickness you'd like. Let's say, just for the sake of this analysis, we assume a thickness of 18 millimeters. We assume that this thickness here is 18 millimeters. Using that information, summing it with everything else, we can come up with our force. Force equal to whatever value. And now, similar to how we did the bolt, we use the formula stress is equal to force divided by area. Our area, again, is this red region. So force Ft divided by that area. That area is the hub thickness multiplied by the length of the key, because the hub is as long as the key. And usually it isn't any longer, because there is no point to having it any longer than the key. Now this stress we will take from our material properties. Our material that we're using here is cast iron. So we will look at the tensile strength of cast iron, and that is luckily given to us. It's given as 8 megapascals. So we'll use that value, we'll substitute it into the formula, and then rearrange it to find our hub thickness. Now this is the hub thickness based on the assumed thickness that we stated. So this is why it is an iterative process, because you have to do a number of calculations to find out which one is the best thickness to use. You can't just do it once and come up with a thickness. You have to do it multiple times to be able to develop a trend. So, okay. So once you've done this formula, you'll come up with a hub thickness. An appropriate hub thickness according to this thickness, according to this force. The force is the one that we calculated from our assumed thickness. Now I'll show you an Excel sheet which demonstrates what I mean by why you have to do multiple calculations. All right, so you're all able to see my screen? So Excel is a very powerful tool, and it's probably the one that you as an engineer will use the most, because it is very flexible and allows you to make small changes to a calculation and run that calculation again very, very quickly without having to do it by hand. So if you can learn how to use Excel, it'll be a great asset to you. So this Excel sheet will basically calculate the appropriate hub thickness. So using the same formulas that we used just now, on paper, I've entered it into the software. Only extra thing it'll do is it'll calculate the factor of safety. All right. So let's enter the same numbers that we did for our previous calculation. So I'll enter again the thickness of 18 millimeters. So 0.018 meters. And it will take into account the yield strength of the material. It'll calculate the force for me, and it'll come out with an assumed hub thickness, or the non-assumed hub thickness, the appropriate hub thickness. And it says that if I'm going to use this assumed thickness, it'll create this much force. This much force will mean that I need an area of this big to be able to withstand the forces. And I'll have a factor of safety at this point. If I use 18 millimeters, a factor of safety of 0.6. Now remember, our factor of safety has to be above 1. Right? So if you then say, okay, I'll use an assumed thickness of 0.02, sorry. So 20 millimeters. It'll say that your area has to be less. You don't need such a big thickness as the previous one, but you still need more than 0.2 to be able to account for this stress, to account for the force. And your factor of safety has now increased to 0.7. So then I say, okay, I want to increase it again. 0.06, let's say, 0.026. Enter, it calculates the force. It tells me that if I use this assumed thickness, the ideal thickness is pretty much the same, and I will have a factor of safety of about 1, almost 1. And a factor of safety of 1 means that the working stress is equal to the yield stress. And that tells me that the minimum thickness that I can have is 26 millimeters. So I need to choose a thickness greater than 26 to have a factor of safety of greater than 1. And that is where you go back to your sheet, your question, your assignment question. And you say, okay, what factor of safety do I want to use? And that is why this table is given to you. It gives you the different factors of safety based on the different situations that you will come across. Now, if you read this, you'll see that for exceptionally reliable materials used under controllable conditions and subjected to loads and stresses that can be determined with certainty, use a factor of safety of 1.25 to 1.5. So that is the kind of factor of safety that I'll be looking for. I'll be looking for a factor of safety of anywhere between 1.25 and 1.5. Going back to my Excel sheet, I'll now increase this thickness so that my factor of safety gets closer to 1.25. Keep going, you find that at a thickness of 0.31 or 31 millimeters, my factor of safety is 1.257 or 1.25, thereabouts. So that's why 31 millimeters is usually will be the ideal thickness. But if I wanted to have a factor of safety closer to 0.5, I could just keep increasing the thickness. Okay, so 0.4, 0.04, so 40 millimeters is too big. So 0.038, it's getting closer. 0.035 is just below 1.5. So my range now is anywhere between 0.031 meters or 31 millimeters and 35 millimeters. Will give me a factor of safety of anywhere between 1.25 and 1.5. The formula for calculating the factor of safety is basically just your tensile stress, so your maximum yield, divided by your maximum stress, working stress. So your force divided by your assumed thickness times your key length, so 0.055. That is the formula for calculating your factor of safety. Okay? And once you've done that equation and you've done these calculations back and forth, you'll come out with a hub thickness. So like I said, hub thickness 31 millimeters. So your hub outer diameter will be equal to your shaft will be equal to your hub radius times 2. Your hub radius is equal to your shaft radius, sorry, plus half key length plus the full thickness plus HT, whole thing times 2. And your hub diameter might come to, say, 120 millimeters. And that is the outcome of your hub analysis. Okay, guys. So unfortunately, we've run out of time. Please just leave your name and ID numbers in the chat. If you're not part of this tutorial session, if you're not part of the 11 to 12 tutorial session, and you're joining from another session, please, along with your name, leave your session that you actually belong to, or the session that you actually signed up for, just so that it's easier for us to track for attendance. And there is a formula for calculating the factor of safety, and that is actually given in the assignment itself. It says here, factor of safety is the material yield strength, or the allowable design stress, is equal to the material yield strength divided by the factor of safety, or factor of safety is equal to yield stress divided by working stress. Working stress is equal to force divided by area. Okay. So thank you very much for attending, guys. I will upload this recording to YouTube and send you all the links so you can have another view of it if you've missed anything. Have a blessed weekend, and I'll see you all next week.